Well, hi, everybody. In this video, we're going to talk a little bit about some other types of counting problems that can come up in a sort of a standard combinatorics context. In my earlier videos, I talked about something called permutations of sets. These would be counting problems where the order of the objects matters and repetition of those objects is not allowed. Here, with combinations, we still are not going to allow repetition, but we're going to say this time that the order of the objects does not matter. So let me write that down. This is the context in which we have repetition not allowed. Okay, so we won't have the ability to repeat objects, but also order doesn't matter. So the order doesn't matter and repetition is not allowed. We're counting arrangements of objects, right? This is what combinatorics is all about, counting arrangements of objects. Those objects can only appear once. And in this section, because we're talking about combinations, we're going to say that the order in which those objects appear doesn't matter. So like if we're talking about license plates or photographs of people, the order or the positions in which the people stand, that matters, right? If you change people around in the picture, you have a different picture and you have to count it as a different picture. But let's think about a different real world problem. What about poker hands out of a deck of cards? When you're holding cards in your hand, you're allowed to, of course, rearrange them however you like. It doesn't really change the essence of what you have, right? So a typical example of something like this would be poker cards. And I'm just going to emphasize here that it would be poker cards from a single deck. The fact that it's only one deck of cards means that you would only see each card one time at the most, right? You cannot have repetition. If I was shuffling together several decks of cards, then we would have to be looking at a case where repetition is allowed. But here repetition is not allowed. So imagine a single deck of cards and imagine those cards being part of a poker hand. You can play them in whichever order you want. That's totally up to you. It makes no difference, right? The order does not matter. Okay, so let's talk about the definition of what a combination is. This is just kind of the background here, but let's write down what a combination is, just for the record here. So let's let S be a set with n objects. Okay, just the background. We're just setting it up here. Suppose we have a set that has n objects. And R combination, this is the word I'm defining, and R combination, I'll underline that because that's the word we're defining, of S is an unordered selection of R objects from S. Okay? So let's just do a quick example of this. Let's suppose I wanted to write down the two combinations. So in this case, R is going to be 2. The two combinations of the set S, let's just suppose that S consists of the letters A, B, C, D, and E. So what we're asking for here are the unordered selection of 2 of these letters, right? So the question would be, what are they? What are they? We're going to list them here. So we're just going to basically grab 2 out of those 5 things. So we could grab A and B, we could grab A and C, we could grab A and D, we could grab A and E, we could grab B and C, B and D, B and E, yada, yada, yada. You guys can write these all down, I'm sure. C and D, C and E, and D and E. Now notice, because it's an unordered selection, I'm not writing down BA or CA as being somehow different. And because they're not different, we're only looking at unordered selections. I don't need to write down BA, CA, and so on. This is all I have to write down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 two combinations of this set S in this case. Okay, there is a very standard notation if we want to count the number of R combinations of a set S. So just by way of notation, the number of R combinations of a set S, right? This is going to be given as follows. It is sometimes written C of NR, or you might even see it like on a calculator button this way with a C with an N and an R as subscripts. Or the even more famous way of writing it is to just put those two numbers on top of each other in some sort of tall parentheses. And the way we read this is N choose R. If we want to say it out loud, if you see this kind of an expression, we're going to say N choose R for that. Okay, it's a combination. So we're simply asking how many ways can I choose R objects from N? We're not putting them in order, and there's no repetition here. Okay. So for example, the value of 5 choose 2 is just 10. We've seen that there are 10 two combinations of a 5-element set, right? So this is a quick example here. 5 choose 2 has the numerical value of 10. By the way, because we're counting the number of ways of selecting some objects from a set, it always has to be a whole number. Okay, so combinations are never fractions. They are never, they're never, anything other than a positive whole number. There's a couple of special cases. I may as well, for the record, write these down for you guys. If I ever wanted to take N choose N, so I have a set of N objects, and I want to know how many ways can I choose all of them. Well, the answer is, you have to grab all of them, right? There's really only one way to do that. So that's just equal to 1. And that's also, let me give myself a little more room here. That is also the same as the value of N choose 0, sort of by convention. How many ways are there to choose no objects from your set? Well, there's just one way to do that, which is literally to not choose any objects from that set. Okay. What other kind of special cases could we have? We could have, like N choose 1. How many ways are there to choose one object out of N that are in a set? Well, pretty natural to just think, well, you can choose any one of the N objects. There's N ways to do that. Or you could actually think of that as the same as if you were choosing all but one object, right? So if I looked at N choose N minus 1, it would make sense that, you could think of this as choosing N minus 1 objects, but you could also think of it as specifically not choosing N minus 1 of the objects, which would be the same as choosing the other object. In other words, one of the one other object that you didn't exclude in the first place. And in fact, this is a general fact. This is a general fact, which is that for 0 less than or equal to k less than or equal to n, it's very well known that N choose k is the same number as N choose N minus k. So if I've got 12 people waiting to play on a basketball team can have 5 players, right? How many ways could I choose the team? Well, I can either choose the 5 players directly that I want to put on the team, just directly choose them. That's 12, choose 5. Again, we're not putting the players in order, and obviously no player is possible to be repeated here. Each person is one unique person. So 12 choose 5, right? That's the combinatorial expression for it. But instead of choosing directly the 5 players that are going to be on the team, I could have just indirectly chosen 7 people that would not be on the team. That would then by default tell you who your team was, right? So 12 choose 5 is the same as 12 choose 7, in other words. Okay, so that's just an example of this fact. This fact can be proven very rigorously as well. I think in order to prove it rigorously, there's actually, we could just do it sort of by common sense. What I just gave you an example that you could generalize. You could say, if I have n objects, I can choose k of them directly, or I can choose n minus k of them indirectly, which is effectively choosing the k that we had in the first scenario. That's kind of a wordy way to give the proof. There's actually another way to prove this that's much more just mathematically formula-based. And to see what that proof is, I'm going to first ask a question that will relate it to what would get us to that proof, which is the following question. How are P of NR, remember, these are permutations. These are ordered arrangements of R objects from among N. How is that related to C of NR? So how are these two numbers related? The permutations, which we learned about before when we have permutations of sets, that means the order does matter, versus when the order does not matter. So let me answer this question, because once I do this, it'll make it easier to sort of, for example, explain a fact like that one. Okay. So here's a good way to look at the answer. Given an unordered arrangement of R objects. So let's suppose that we have chosen R objects, but we have not yet put them in order, right? What if we would then want to put them in order, right? Given this unordered arrangement of R objects, we have, well, now if we're going to put them in order, we're going to make slots, right? We're going to have a first slot, a second slot, a third slot, a fourth slot. They're going to go in order now. So that first slot, I can put any one of the R objects. The second slot has R minus 1 remaining objects. The third slot would have R minus 2 remaining objects that still haven't been placed that could be chosen, right? It's a factorial, right? We would have, in fact, R factorial ways to then put them in order. In other words, if I want to take a combination and turn it into a permutation, right? Then what I'm basically saying is that if I want to know how many ways could I have a permutation of the R objects, that would just be R factorial possible rearrangements of a combination of R objects, right? So this is the number of ways to get an unordered choice of R objects from a collection of N, from a set of size N. This is unordered objects, R of them. Then I have to put them in order. It's almost like the multiplication principle, yeah? So we first select the 5 members of the team, right? And then we would have 5 factorial ways of then placing them into positions on that team. And that would then give us the number of ordered teams of 5 for the basketball game, right? So that's basically the relationship between the P of NR and the C of NR. And so in particular, I can take C of NR, I can solve for it here. P of NR, I can divide it by R factorial. Okay, just moving things around. And then if I remember how the works, that was actually, so I'm going to put the 1 over r factorial here in the front. You may remember the formula for P of nr. It's just n factorial divided by n minus r factorial. Okay. So this, my friends, is actually a numerical formula. This is giving me now a numerical formula for the number of R combinations of an n element set. Okay. Hopefully that makes sense so far. Feel free to pause, jot down any questions you have. You can certainly send those to me. Be glad to look at those. So guys, take a look here at this fact. So the proof of the fact above, I already gave you sort of one proof. But now I'm going to give you another one that we can actually just do it with the formula, right? So n choose k, right? According to what's on the bottom of the board down here, that is just n factorial divided by k factorial and n minus k factorial. But you see, if I replace the k with n minus k, imagine everywhere you see a k in this formula, you change it to n minus k. Don't you end up getting just the same thing with the 2 factorials reversed in the denominator? It's exactly the same thing. So that's it. It's just like a quick little numerical calculation. But honestly, the common sense way of thinking about it is also totally, totally good. Equally acceptable. Okay. Now that we have this sort of combinations formula, we have n choose k, the number of ways of making an unordered collection of k objects from n. We can actually start to think about some other combinatorics ideas using combinations as a tool. There is a well-known formula for the number of subsets of an n element set. So I'm going to just show you this as kind of an application. So let's suppose that we have a set whose size is n. The question would be, how many subsets does S have? How many ways could we make a subset of those n objects in the set S? Well, there's actually 2 different ways of thinking about it. So answer number one, and this is really the simpler answer, is to just simply say, look, for each of the n objects that you're talking about in the set S, when you want to build a subset, each of those objects is either in that subset or not in that subset, right? There's 2 choices, in or out. So the first object, either in the subset or out of the subset. The second object, either in the subset or out of the subset, right? 2 choices, 2 choices, 2 choices. Every single object has 2 choices. It's either in the subset or it's not in the subset. That is simply going to be 2 to the n. And we can just say, if we want to give a little reason here on the side, each object in S has 2 choices, in or out. Of course, we're using the multiplication principle here. How many ways to totally make this subset? Well, we have to go through each task with each object and decide yes or no. So we're multiplying each of those options together. So that's where the 2 to the n is coming from. This has nothing to do with combinations so far, but I want to give you a second answer if you're ready for it. If you're not ready for it, you should be pausing the video and do yourself Maybe you could even take an example, choose a small value of n, like n equals 4 or something, write down a set A, B, C, D, and think about making subsets of that. Each of the letters in that subset is either in, each of the letters in the set S is either in the subset or out of the subset. That's what you have to think through. Okay. So you can make this a little more concrete if you need to stop and look at an example. And I encourage you to do that if you're kind of puzzled about this 2 to the n. But there's another way to think about counting all of the subsets of S. You see, guys, a subset is an unordered choice of some of the objects from S. And we're assuming, again, that these objects are all distinct. There's no repeats. And so it's an unordered collection where repetition is not allowed. If I want to make a subset of size K, I have to choose K elements out of S to put into that subset. And there's n choose K ways to do it. Right? So in other words, what we can do is we can just say the number of subsets of S of size K is literally n choose K, because again, the set S has n elements in it. We're going to choose an unordered collection of K of them to make my subset. That would be subsets of size K, and guys, K could be anything. Could be 0, could be 1, could be 2, could be 3. So if we now sum, so summing over K, K could be as small as 0 or as big as n. We obtain, well, it's just going to be n choose 0 plus n choose 1 plus n choose 2 and dot, 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 so on and so on and so on, all the way up to n choose n. This is also the number of subsets of a set S of size n. So we've answered the question in 2 different ways that were completely different from each other, right? 2 different ways that were completely different from each other, but we know that we're answering the same question. How many subsets does S have in total? So you know what has to be true about the 2 answers then? We have actually just proven something. This proves what I'm going to say, that we're proving it combinatorially. This proves combinatorially that, and we're going to state this as a theorem down here. Maybe some of you already knew this result, but it's kind of neat to see it in writing. On the left side, I'm going to write 2 to the n. And on the right-hand side, I'm going to write n choose 0 plus n choose 1 plus n choose 2, and so on, dot, 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 all the way to n choose n. That is a theorem. Now, unlike the n choose k equaling n choose n minus k, this one we could prove very easily just using the numerical values, the factorial expression of n choose k, right? We could just use that formula pretty simply. Think about this theorem, though. If you tried to take the right-hand side and like write out a bunch of factorials on that side and somehow expect the algebra to somehow magically give you 2 to the n, that sounds a lot more daunting to me. That sounds a lot more daunting to me. So it's actually a really nice type of proof that we've introduced here, guys. And we're going to be doing more of these later. But we have done a combinatorial proof of a formula by basically choosing something to count. In this case, how many subsets does S have, right? We have done that in 2 different ways that seem totally unrelated to each other. And yet we know that whatever the answers are that we come up with have to match. It's pretty neat. It's pretty neat. Okay, great. I'm hoping that so far, so good. Let's just do a few more practice problems, just kind of get some more real world examples that involve combinations. Now, on some of these examples, we may also be using permutations. Permutations tend to have the factorials in them a bit more often. The combinations, of course, we see the n choose k all the time. So we may see some of all of that in here. But I just think it's good to practice, especially as we start getting more and more of these sort of combinatorial flavored quantities in our wheelhouse. I think it's good to practice a little bit how these things could work. So let's just do a few examples here just to practice. And as I'm doing these examples, guys, feel free to pause my video and try them for yourself first. Okay, there's no harm in giving it a shot, and then you can just resume the playing of the video and just kind of see what I had to say about it. Okay, so here's what we're going to do. We're going to ask the following question: how many 5-card poker hands? As soon as I see that, I'm already thinking that order does not matter. How many of them, how many 5-card poker hands contain? I'm actually going to do several parts here. So there's going to be several parts to this. So let me just start with part A. And in part A, I'm not going to put any restrictions whatsoever. I'm just going to say, how many 5-card poker hands are there, period. Okay, let's just leave it at that. Okay, well, we do have to remember that a full deck of cards is 52 cards, right? There's 4 suits, 13 types within each suit. So that's 52 cards in a regular poker deck. I hope everybody just kind of knows that as a standard fact. And what are we doing here, guys? We are simply choosing 5 of them. There's no restrictions. We're not saying what 5 we can choose. We can just literally pick them at random. So the answer here, I don't even need much explanation for this one, guys. The answer is literally just 52, choose 5. That's it. Of course, this has some numerical value. If anybody wants to figure it out, you can. In fact, maybe just to point this out, I'm just going to write it using factorials for a moment. You know, so this would be the formula for n choose k with the appropriate numbers plugged in. You'll notice that you can really cancel a lot of these factorials. The bottom has a 47 factorial, which actually cancels most of the 52 factorial. The only thing that doesn't cancel would be the numbers above 47. And then we have on the bottom the 5 factorial. So actually what I've shown you here is a kind of a nice little trick. When you're doing like n choose k, you sort of have factorials on the top and on the bottom that go the same distance down. Notice that I'm factorialing down 5 steps from 52 on the top, and I'm factorialing up from 1 by also 5 steps on the bottom. So this is not some accident here. This is actually always going to work out this way. So if somebody, you know, wanted to know what is 52 choose 5 and you didn't have a calculator around, this would be the way to sort of get to the answer the fastest, because you've gotten rid of a lot of stuff that cancels from the very beginning. So anyway, I think that was just worth pointing out. If you've never seen that before, it's good to know that. Okay, let's try another example. How many 5-card poker hands contain 4 of a kind? So that might be 4 kings or 4 aces. It could be 4 sevens, right? So we have to remember, what do we have? We have 13 different kinds. They are ace, king, queen, jack, and then 10, let me just get this right. So ace, king, queen, jack, 10, 9, 8, 7, 6, 5, 4, 3, 2. So there's 13 different kinds here. So actually, that's kind of part of the answer to the problem, is that we have to choose a kind. There's 13. Choose kind to have 4 of. Okay, and then after we've done that, we just have to choose any other card. So a 4 of a kind hand, remember there's 5 cards in total that are in your hand. You're choosing 4 that are all of the same kind. Maybe you chose all 4 aces. And after you've made that choice, there are only 48 other cards left, right? You started with 52, but you're getting rid of the 4 aces. And now you just have 48. Any other card will do, right? So this would just be choose another card. Guys, I like on answered, again, I don't need this simplified here, but I do like to see, okay, where did the 13 come from? Where did the 48 come from? Just a quick little note to explain your answer there. That's a really, really helpful thing to do. Okay, let's go ahead and come down here and do another one. What if I wanted to have part C, exactly 2 suits? Okay, so remember, suits is not the same thing as kinds. The kinds are like aces, kings, queens, jack. The suits are, you know, the diamonds, the hearts, the clubs, and the spades, right? Not much of an artist, but I try. So anyway, there's 4 different suits, and we're asking how many ways are there to make a 5-part card poker hand that has exactly 2 of those 4 suits in that hand. Again, feel free to pause the video for a second, think about it for yourself. What are the tasks that you would have to do to put together a hand that satisfies this requirement? Underlying everything here is the multiplication principle, right? We're breaking down the process of building my 5-card poker hand into a bunch of subtasks that together comprise the full task. I think if I was doing it, and again, this is the place to pause it if you don't want me to spill the beans too soon, but I think that the way to tackle this problem is to first choose, and because we're talking about poker hands, they are not ordered, but to just choose the 2 suits that you actually are going to work with. Okay, so this is choose the suits. Okay, so we'll start with that. That's the first task. So I don't know, maybe you end up choosing diamonds and hearts, whatever. You choose 2 of the suits. Now, you have to pick at least 1 card from each of those 2 suits that you've chosen, right? You have to have at least 1 card from each of those 2 suits. So what could it be? Let's say that it is diamonds and hearts. So you could either pick 4 diamonds and 1 heart, or 3 diamonds and 2 hearts, or 2 diamonds and 3 hearts, or 1 diamond and 4 hearts. Any one of those 4 things, and we need to actually add those all up. Those are different cases that we could have. So 13 diamonds, we could choose 4 of those, and then out of the 13 hearts, we could choose 1 of those, right? So I could just put here maybe diamonds and hearts, something like that. And then the next one would be, what if we had only 3 diamonds, but we had 2 hearts? Okay, or we could have 2 diamonds and 3 hearts. Or finally, we could have just 1 diamond and 4 hearts. All of that is in brackets. That way you're making sure that you actually get at least 1 diamond and at least 1 heart. You see, you can't just say, well, there's 26 cards here, let's just choose 5 of them, because you could accidentally choose 5 hearts that are all hearts, and then you haven't used both the diamonds and the hearts. So we do have to be a little bit careful, right? Great, so that's the answer here. And again, I don't care what the numerical value is. I care much more about just understanding what each term, each expression represents in the answer that we have there. Okay. Take notes on these, guys, and if there are questions, you want to talk about any of these later, we certainly can. Let's do a couple more. Okay, we're just practicing. This is just practice right now. How many 5-card poker hands contain all 4 suits? That's a good one. How many contain? So you know you have to have at least 1 diamond, 1 heart, 1 club, and 1 spade. But what we do know is that there's 5 cards total. So one of these suits, exactly one of them, in fact, we would have to have 2 cards from, right? Because there's an extra card compared to the number of suits. So one of these suits will be represented twice. Let's choose which one that is. Choose suit or 2 cards. We have to choose one. We don't know which one it's going to be, but that's a choice that we have to multiply into our answer. Let's say it's hearts. Let's say we've got 2 hearts and then exactly 1 diamond, 1 spade, and 1 club. I bet you can fill out the rest of the answer now. You just have to choose from each of those 4 piles the appropriate number of cards. So there would be 13, choose 2 for the hearts, if you chose that hearts was going to have 2 cards from. And then the other 3 suits, you would literally just choose 1 card from each of those suits. So this is choose cards from the 2-card suit. And this is just simply choose 1 card from all other suits. So I just need, hopefully you're getting the idea through my lectures here, kind of what I'm expecting in terms of like an explanation. We don't just want numerical answers. We also don't just want the combinatorial expression of the answer with no explanation to it. Okay, let's do one more and then we'll set down the poker cards for today. Call this one part E. Let's see what we can come up with here. How many 5-card poker hands contain at least 1 club? So I'm going to start off by presenting with you guys with an answer that doesn't quite work. And let's see if we can. So you don't need to write this one down because what I'm about to write here is actually not correct. But maybe we could write something down and we'll just kind of see if you have any ideas why this does not work. So here's my reasoning. I'm going to start off by grabbing a club because I know I have to have at least 1. So I've got 13 clubs I could choose from. I'm just going to grab one of them. And now, at this point, I just need 4 more cards, and they can be anything I want. So out of the remaining deck of, so we grabbed 1 club to begin with. Now there's 51 cards left. 13 of each of the other suits, and there's 12 clubs left. 51 cards left total. I'm just going to grab any 4 of them. Seems like that should be okay. But there's actually a problem with this. The problem with this is that you are somehow, so we're going to end up with at least 1 club, but maybe additional clubs over here, right? I mean, we could choose more than just 1 club. But by choosing one of the clubs first, we are putting it in order. We are making it special. This first club that we're picking, maybe we pick the ace of clubs, right? And then maybe over here, we later on will pick a king of clubs. So we've got an ace of clubs and a king of clubs. The problem is I chose this ace of clubs first. It was in order as part of the first task. And then in the second task, we got the king of clubs. And that should not be counted as a different poker hand than if I had first grabbed the king of clubs and then later on picked up the ace of clubs when I chose the other cards, right? So this is actually not going to give us the right answer. It's a tempting answer, but it doesn't quite work. Okay, so let's be real careful about this. Maybe pause the video now. Think about what would be a correct way to figure out poker hands that have at least 1 club. Just going to erase this. go ahead and pause the video and think about it. How many poker hands have at least one club? Okay, I'm going to suggest that we do this with the subtraction trick. Maybe that's what you were thinking. In other words, we could count how many poker hands have no clubs and take them away from the total. The total, remember, was 52 choose 5, right? That's all poker hands with no restrictions. And I can subtract, so this is all poker hands. And I can subtract away poker hands that have no clubs. So what happens if I take all 13 clubs and just remove them from consideration? Doesn't that leave me with 39 cards left from which I can just choose any 5 of those? That's exactly right. And that does give us the correct answer. So this is poker hands with no clubs. It's a little subtle, isn't it? In this case, whenever I see that at least one question, I tend to be thinking about whether I could use the subtraction trick. Take the total and subtract violations, the hands in this case that have no clubs. That works really nicely. So you should grab a calculator and compare this answer with the false answer that I proposed earlier that doesn't actually work. And you see that they're not the same. Okay, let's put down the poker cards for a little while. I'm going to take a breath here. I'm going to erase my entire board and we're going to practice with some other examples. Okay, so I'm perfectly content right now to just practice permutations and combinations. I want everybody to get really good at this, okay? And although we're not using a lot of heavy-duty math, there's not a lot of deep theorems here. You know, it's not like we're doing any particularly like important prerequisite knowledge into these problems. You're seeing, I think, that some of these are a little subtle. And so it does take a little bit of practice to kind of get your mind tweaked into how to think about these things. So that's why I'm not rushing this. I want to take a good amount of time to play with these examples. Let's take a different kind of problem. We'll leave the poker cards behind. And let's start off this way. From a group of 6 men and 8 women, we have 14 people. There are 6 men and 8 women. We must form a committee of 6 persons. Okay. We're going to make committees of 6 people from among the 14 people that we have at large here. So here's the question. How many ways can we do this if the following, so we're going to do a few cases here as well, if that's all right. All committee members are the same sex. So we either have all men or all women, right? So let's start with this one first. It's kind of a nice little problem to get started with. Now, again, we're just forming committees. It's like forming basketball teams. We're not putting anybody in order here. We're just choosing the people, right? So in this case, we have 14 people to choose, but the answer is not 14 choose 6 because we could end up with committees having some men and some women on them, right? We need to make committees that are either all men or all women. And that sounds like 2 cases that we should combine with the sum rule, right? That's exactly what we're going to do. How many ways would there be to make a committee of all men? We have 6 men, and we want to make a committee of 6 men. that is just one way, right? We have to take all 6 men and put them on the committee. Now, I'm going to write it as 6 choose 6. But as we saw earlier, n choose n is just 1. So this is one way of doing this. What if we made our committee by choosing from the women? Now, this time we have 8 women, and we're just going to choose 6 of them. Okay. This would be a perfectly good answer. So this would just be, just to give me a little clue as to how you got the answer, this would be all men. This would be all women. If we wanted to simplify it, of course, 6 choose 6 is just 1. Now, 8 choose 6 is the same as 8 choose 2. And I'm going to do that little falling factorial trick. Because it's 8 choose 2, which is the same as 8 choose 6. I only have to factorial 2 steps, right? So it's just this. The 8 and the 2 go in 4 times, and we come up with an answer, a total answer there of 29, if I did that right. Okay. Let's do another part here. Let's try again. The committee must have more men than women. The committee must have more men than women. It's a committee of 6. So if it's going to be more men than women, wouldn't that be, well, what could we have? We could have 4 men and 2 women. Or we could have 5 men and 1 woman. Or 6 men and no women, right? So there's those 3 possibilities. Let's just add the 3 possibilities up. So what if we're going to have 4 men and 6 women? Won't we just choose the 4 men from the 6 men that we have, and then out of the 8 women, choose 2 of those, right? So this would be 4 men, 2 women. Or we could choose 5 men and 1 woman. So that's the second case. Or we would have to choose all 6 men and choose no women. That's actually only one way to do that, right? This is actually just 1 times 1 here. This is just 6 men. The whole committee is just men. There's the answer. You just have to kind of add up all of those terms. Okay. Fantastic. I hope this is making sense so far. Let me go ahead and erase a little bit here. Go a little bit further. Let's do a totally different, I'm still going to take 6 men and 8 women, but I'm going to ask a very different question now. We're not going to make a committee anymore. This one's a little bit more interesting. How many ways, again, this is just more practice, guys. I don't want to be accused of not doing enough practice with you. So I'm seeing lots of examples here. How many ways can we seat? In how many ways can we seat 6 men and 8 women? So again, we have 6 men and 8 women. Whenever you have something like this, of course, you're assuming that there's no repeats. Unless the problem had identical twins or something like that, you don't have the same man twice. You don't have the same woman twice. No repetition is going to be allowed here. But this time, the thing that's a little interesting, though, is that unlike choosing committee members, or choosing suits or kinds in a poker hand, when I start to see a seating arrangement, it starts to feel like it's going to be somehow in order, like the order is going to matter here. So this might be an example where we're going to combine a little bit of combinations and permutations together, right? So that often happens, right? So how many ways can we seat 6 men and 8 women in a row? Now, if I just stopped right there and I just said, that's the whole question. This is not where I'm going to stop. But if I stopped with just that, how many ways can we seat 6 men and 8 women in a row? There's no reference to why somebody has to be a man or a woman in a particular seat. So you have basically 14 slots or chairs, and you have 14 factorial ways to just set people down however you would like. And that would be the answer, yeah? So if we didn't care about anything else and it just said, how many ways can you put 6 men and 8 women in a row? I might as well have just asked you, how many ways can you put 14 people in a row? And that would just be 14 factorial. It's just the permutation, right? But we're going to add a little twist here. If no men can sit next to each other. That makes this problem totally different. No 2 men can sit next to each other. We should never see a man next to another man. So between these 6 men, there always has to be women seated as well. Between any 2 men. So you might think, well, I'm just going to scribble here. You don't need to write this down yet, but let's just think. You might just be thinking, well, I could set my 6 men down somehow in some seats in this row. And now I just have to make sure that I put a woman, in between. But the problem is that we don't just have 5 women. We actually have 8 women, which means that we could also put women over here, or we could even put multiple women in some of these places, And that gets to be a little unwieldy as to how to count that, right? I mean, you're going to have at least 1 woman here, 1 woman here, 1 woman here, and 1 woman here, but you could have all the other women right here. Or you could have some of them here, some of them here, and some of them on the other end. It's too messy to sort of analyze that. So setting the men down and then trying to put women in between them leads us to an analysis that's not very simple. There would be too many cases. It would be hard to make sure you covered every case that there was. And I think there's surely would need to be a better way, right? So let's try something different. Let's do it this way. Let's actually set the women down first. Let's see what that would do. So we have 8 women, woman 1, woman 2, woman 3, woman 4, woman 5, woman 6, woman 7, and woman 8. And of course, I have to choose which woman goes in which position here. There looks like there'd probably be some kind of an 8 factorial, just with if I just think only about the women from left to right, we're going to have to put those women in order. So I'll do that, but I want to first just get the configuration of men and women figured out. Okay. The thing that's the clever trick here, guys, is that in each space that I have created, and I've created a space in the front of the first woman and then between all of the other women, and then there's another one over here at the very end as well. Sorry, a little bit tight on space, right? In each of those spaces now, I can only put 1 man, right? So unlike when I put the men down first and then thought about putting women in between, I thought, well, I could actually put several women in some of those places. Here we know that if we put 2 men in one of these positions, these spaces, these slots that I've drawn, then we've got 2 adjacent men, and that's not allowed. We're supposed to find arrangements where no man is sitting next to another man. So what we're saying is that each one of these spaces can have at most 1 man. We have 6 men total, and how many spaces do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 places where a man could sit down now. But once the man has sat there, no other man can sit in the same spot again. So you know what we're going to do with these 9 spaces? We're going to start by choosing 6 of them to put the men in. I love this solution. It's really clever, right? 9 choose 6 ways to choose which spaces in the figure above, so I hope you guys have drawn this little picture, will be taken by a man. So maybe a man is going to sit here, maybe no man sits here, maybe no man sits here, maybe there's a man here, maybe there's another one here, another one here, and another one here, and maybe nobody sits in the far right space. That's a choice. That's one of these 9, choose 6 possible choices. We're choosing the seats that those men are going to occupy. What we've done, if we stop with this answer right here, is we've simply chosen which chairs will be occupied by men and which ones will be occupied by women. We have 14 chairs, right? We now know that the first chair has a man in it, the second one has a woman, the third one has a man, the fourth, fifth, and sixth one have women in them, and so on, right? So we've made that determination. The 9 choose 6 sort of fixes that. So what's missing here? What have we not done yet that we still need to do? Well, we need to actually choose which man goes in which of the 6 men's seats. We have 6 men and we have now 6 seats for them. Right? So there would be 6 men with 6 factorial ways to put them in those seats, right? So we're seeing permutations and combinations right together in the same answer, right? So there's this many ways to choose men for their seats. Which seats they're going to have has already been decided, but now we have to actually put those men in those seats. And then we, of course, have to do the same thing with the women. 8 factorial ways to choose the women for their seats. And we have 3 subtasks here that lead us by the multiplication principle to the final answer. So that's the final answer right there. I guess one of the things I want to just say about this, guys, is that when order matters, we're sort of thinking about these factorials. And when order doesn't matter, and we're just choosing things, we're not putting them in order, we tend to think about combinations. So we have combinations and we have permutations, and we see that both of them are kind of appearing in this answer. The issue is with a problem like this, it's just not as clear cut. We can't just say, does the order matter here or not? It's that question does not get to the essence of how we're going to try to solve this problem, right? We actually have to think about it in subtasks, and within each subtask, we have to ask ourselves, does the order matter? It sort of matters which man goes in which man's chair and which woman goes in which woman's chair, but in sort of arranging the men's and women's seats in the first place, before anybody sits down, the order really doesn't matter. We just have to choose in an unordered way which 6 chairs the men are going to sit in, or equivalently, which 8 chairs the women are going to sit in. So anyhow, so that is a little bit more, I would say, of a slightly more tricky kind of problem, but certainly very doable. Okay, great. I'm just going to take a couple minutes and kind of just introduce the next topic. We won't have time in this video to do a ton with this. This video is mostly about combinations of just sets. So no repetition and order doesn't matter. If we want to go to the sort of the opposite extreme of that, we would go back to permutations again. Permutations is where the order does matter, right? And instead of sets, we could do permutations of what are called multi-sets. Permutations of multi-sets. A multi-set is going to be where we are allowed to have the same object in the set more than once. So here, in that case, this means that repetition is allowed. And because it's a permutation, order matters. It's kind of the opposite of what we were talking about for most of this session. So just so we are all clear about what a multiset is, a multiset is just a set. A multiset is just a set whose objects need not be distinct. In other words, you can repeat the same object more than once. That's basically what we're getting at here. Just as a little bit of a notation that we'll use when we talk about this, if object X occurs, let's say, n times in the multiset, if it's repeated n times, you'll see me do things like this. We might write n times x, right? So that's not literally a multiplication, okay, because we're talking about an object here. The n dot, the object, just means that object is in there that many times. So just as a quick example, if my multiset S had, A, B, C, 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 right? So here I see that the objects are not all distinct, but I can see that I have 3 A's. So I'll write 3 dot A. I have 2 B's, just 2 dot B, and I have 4 C's. So 4 dot C. That's a simple example of a multiset. Sometimes your multiset may have an unlimited number of objects. So I should also just point out a little bit more notation. You might have the same object an unlimited number of times. So if X occurs an unlimited number of times, you won't be surprised how we're going to write that. We are going to write literally infinity times x. So we're really abusing notation now when we write things like that. So that's a notation for this multiset, basically. So let me just see, what else do I want to say here? Maybe I'll just write down a quick theorem and then we'll just about wrap this up for today. So this is just notation for multisets. So there's a quick little theorem here in terms of what the counting would look like. Let's just state this one and maybe we'll do a quick example of it and then I'll call this good. So let's let S be a multiset with K different types of objects. So let's just suppose that there are K different types of objects. Let's suppose that each of them is with infinite repetition. So we have infinitely many A's, infinitely many B's, infinitely many C's, and so on. We can take as many of each object as we want, right? It would be like if we were making license plates of any length whatsoever that we wanted. We could grab the same letter as many times as we wanted. We would never run out of letters, right? The license plate could just be X, 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 however many slots there were, right? We would never run out of letters there. So if we have that setup where we have K different types of objects and we want to make an R permutation, so this is what I want to talk about. The number of R permutations of S. How many R permutations? That means we're going to make something of length R. But there's no limitations on the repeats, right? We can repeat things as many times as we want. That means in each of these R slots, these are my slots, right? Imagine it goes on, there's R of them here. Suppose I've got R slots right here, right? Well, I can put any one of my objects in each of those slots and I can repeat it again and again. So instead of seeing a factorial on this one, what we're going to see is just K raised to the R power. It's just that simple, right? K times K times K times K. It's just a bunch of Ks multiplied together. So that's basically the theorem. It doesn't really need much of a proof. It's kind of just common sense using the multiplication principle. So I mentioned license plates, for example. That just is a really simple example of this theorem. The number of 7-letter license plates. See, because we know that unless they tell us that the letters have to be distinct. If the letters have to be distinct, that's a different story. But they didn't say that here, and we know that we have an alphabet that has 26 letters in it, and we can use any of those 26 letters as many places and as many times as we want, right? So this is simply 26. That's the number of different types of objects that we have when we're filling out letters, assuming we're using our English alphabet. And the power, the R, is just the length of that permutation, which in this case, it's 7. So this would just be the answer, okay? And then, something like this doesn't need a lot of explanation. Of course, it never hurts to draw the little picture here. You can draw 7 slots and just put the number of choices. Each slot is going to have that same 26 choices each time. Okay, 26 to the 7. Okay, maybe I'm going to write down one more problem, but I'm not going to solve it in this video. I'm going to leave it until next time. But this is one that you can think about. And let's see what you think. A witness, this is a word problem. A witness to a hit and run accident reports that the license plate, they caught some information about the license plate. It consists of 3 digits followed by, so the 3 digits come first, and that's followed by 3 letters. So there's more information here. Contains a 4, so they definitely saw a 4 on this license plate, and a 9. So they saw both a 4 and a 9. We don't know where. And that there were, this is kind of silly, but let's assume that he could see that there were no vowels. A, E, I, O, and U are the vowels. So there's 21 other letters among the 26. So the question is, how many plates are possible? We could have tried to solve this problem even before we had the little talk about mini sets or multi-sets, but that's okay. I think it's still, this will be a good time to think about it in the context of the theorem up here. The multiplication principle, of course, will play a role. And having to do a kind of a careful analysis of several subtasks that make up this problem. So give this one a try. And next time we get together, I will come back to this problem and we will work on it together and see if we're all in agreement about what the answer might be. Or you can put the answers down in the comments to the video as well. That's also fine. Thank you guys so much for watching. I think we're going to say more about multi-sets next time. But for now, I think this is a good start. Thank you so much for being here. And I hope that things have been making sense. Let me know if there's anything I can help with or if you have any questions. Bye for now. We'll see you again very soon.